so if you see this diagram, we'll have so the entire project can be written in just one module. So in the previous lab 0, we have two modules, DFF and counter. For this project, for division, this project, you can just have one whole module in your source file. So the logic here is, so these are, so I just converted these paragraphs into points. We can understand this using this. So we'll have three registers: register B, register R, and register Q. So this is so the register B, register R, and register Q. Q and R for quotient and remainder. So initially, what we would do is, the A that is given to us, we will assign that A value to our register Q. And then we have a subtractor module. So what subtract? So the subtractor module takes the partial remainder and subtracts B from it. So what is the partial remainder? So the partial remainder is register R. Okay. So in order to understand these diagrams, just keenly follow these lines. So if you see these lines are coming from this register R module. So we take all these things. So register R is 16-bit. So 0 to 15 of that, and we take 1 bit from register Q. That is the last, the most significant bit, 31st bit. So this is one input to the subtraction module, and the other input is your B. So B is also 0 to 15. It is a 16-bit number, and we are appending 1 0 at the most significant bit. So in this in the subtraction module, you are taking register RQ31. From this we are subtracting our B value. So this is with respect to subtraction. Now once you get an output, we will see the most significant bit of the output. If the most significant bit of the output is 0, so this is the most significant bit which is given to the multiplexer. So depending on if it is 0 or not, so if it is 0 or not, we will have different outputs from the multiplexer. So one of the input to the multiplexer is your register R. So register R 0 to 14 and Q31. So if you see these lines, we are taking this Q31 into this multiplexer, and the remaining bits are 0 to 14. The 15th bit is neglected. Register R 15th bit is not given to the multiplexer. It's 0 to 14 with a Q31. And the another input to your multiplexer is subtraction, the output from the subtraction module, that is 0 to 15. I hope this is clear. So we have two inputs, which each one of them is 16-bit. Depending on the subtraction output, if it is 0, we'll select one of them. If it is 1, we'll select another one. So if the result of the subtraction is negative, the multiplexer will select this one. If it is positive, the multiplexer will select the subtraction output. So this will be your register R. This is how you assign value to your register R. And then for the register Q, you'll have 0 to 30 of your Q, and the 0th bit, the least significant bit, is nothing but the negation of the sub output most significant bit. So okay, 1 bit of Q is obtained from the sign bit of the subtractor result and returned to the LSB of register Q. So this is the sign bit, the most significant bit. This is negated and it is set as Q of 0. So this will become the 32 bit Q. So I just converted this paragraph into these points. That's all. So first we'll assign A to register Q, B is B, and register R is 0. Then we will do a left shift. So left shift is nothing but taking one one bit from the removing the most significant bit from Q. So these values are given to the subtraction module, and we subtract B from it. So the output from the subtraction module is used to decide what should be the mux output and what should be assigned to our register R. And it is also used to set the least significant bit of Q. So this is the crux of this one. When you come to the so your test pen should have clear start clock A and B. So these are our inputs. Clear start clock A B are the inputs, and Q are the outputs, and busy ready count are also they are not final outputs, but they are just used internally, so you can display them as well. So so this paragraph I try to explain it over here, or here I'll go through it. So start signal, so if your start signal is set to 1, that means you're supposed to start the division. The busy so busy ready are something which we have to set in our source code. So depending on clear and start values, if clear is 0, your busy is 0 and ready is 0. If clear is set to 1 and if your start is also 1, then you have to start your division. That means the module is busy now, so you have to set it to 1, and ready is 0. So ready here indicates whether the outputs are ready or not. Is the division completed or not is specified by the ready variable. So once your busy is set to 1, we have to start performing the division, and so we need to keep iterating. We have to do these steps for 32 times. So our uh, so it's just the length of our A, so we have to do that 32 times. So to keep track of that, how many times we have performed it, we use this count variable. So once this count variable reaches 32, we set our busy to 0, that means the division is over, and we set our ready to I'm sorry, we set our ready to 1, so the outputs are ready. Now you can check the outputs once the ready becomes 1. So Q and R are ready. So this is the uh, uh, this is how you are supposed to use these variables and perform division. So the report submission and other stuffs remain same. We have to use the same the device number. You have to take screenshots of your simulation. Uh, so the synthesis, IO planning, and floor planning. So along with your Verilog code, you are supposed to place all this in your uh, report. So if anyone have doubts regarding this restoring division, you can